everyone, this is Akriti and I will be talking on the statistical properties of the radio-infrared relations in the SN1 field. In star-forming galaxies, the dust around the young massive stars radiates in infrared wavelengths that are used as a good tracer of star formation rate. On explosion, these stars turn into supernova, which oscillates the cosmic ray electrons in the presence of magnetic fields of the galaxy, thus emitting in the radio synchrotron emission. Therefore, radio emission is used as an extinction-free tracer of star formation. A strong correlation is observed in the literature for the radio-IR relations, which can be quantified by the two parameters given here, the slope B and the Q values. The B can be nonlinear depending on whether the energy copartition between the magnetic fields and the cosmic rays are valid or not. We also note that Q depends on physical parameters such as the number density of UV photons and cosmic ray electrons, dust temperature, magnetic field, and spectral index. Thus, this can give rise to nonlinearity observed in the radio-IR relations.
We have used various standard multi-wavelength study to identify star-forming galaxies and AGM in the SN1 field. For K correction in radio wavelengths, we have modeled the radio spectrum as a power law, while we have modeled the infrared SED by using a combination of modified blackbody and a power law with a cutoff. We find that Q24 values to increase with redshift. These sources have higher dust temperature, and with this, the peak of the dust emission shifts towards the shorter wavelengths, resulting in an increase of Q24 values. However, this variation is mild in case of Q70 micron because it is relatively less affected by the variations in dust temperature. This shows that the dust temperature introduces bias in flux-limited near-infrared selected sample. Further, we observe a good correlation between radio and infrared luminosities with nonlinear slope values in all the three cases. We find that the radio-infrared relations are tighter when studied for the bolometric luminosity. This is expected because the infrared luminosity, when integrated over the infrared spectrum, is independent of dust temperature, therefore removing the dust temperature variations in the Q parameters. Although other variations like the magnetic field and spectrum still persist. Therefore, to avoid the spectrum variations, we now derive the integrated radio bolometric luminosity in the frequency range 100 MHz to 2 GHz. We find that the slope is still superlinear, and most importantly, this analysis doesn't improve the scatter in the radio-IR relations significantly. Hence, from our study of the radio-IR relations, we find that the radio spectrum or D-dust fluctuations does not affect the radio-DIR relation. This implies that the other factors, including UV photon density, cosmic ray electron density, or the magnetic field, may affect the scatter in the radio-IR relations. These are the small summary of this work that is under review. Thank you.